How does measurement collapse quantum superposition? Imagine a tiny particle that can be in many places at once, like a coin spinning in the air. This strange situation is called superposition, and it's a core idea in quantum mechanics. When we look at the particle, suddenly it chooses just one place or state. That moment of choosing is called measurement, and it causes the superposition to collapse. But how does this happen? Let's explore. Before we measure, the particle exists in a blend of all possible states, described by a wave function. This wave function is like a recipe that tells us the probabilities of finding the particle in each position or state. It evolves smoothly over time, following a rule called the Schrödinger equation. This rule predicts how the wave function changes, but it doesn't tell us when or how the superposition ends. When we make a measurement, something different occurs. The wave function suddenly jumps from being spread out over many possibilities to just one. This jump is called collapse. It's not a gradual change but an abrupt switch. The outcome we get depends on probabilities. The chance of the particle ending up in a particular state is related to the size of that state's coefficient in the wave function, specifically the square of its magnitude. Different ideas try to explain why collapse happens. The most common view, called the Copenhagen interpretation, sees collapse as a fundamental part of measurement itself. It treats the act of observing as a special process that causes the wave function to reduce. Another view, called the many worlds interpretation, says there is no real collapse. Instead, all possible outcomes happen, but in different, branching universes. There are also theories suggesting gravity might cause collapse, but these ideas are still being tested. A related concept is quantum decoherence. When a quantum system interacts with its environment, like air molecules or photons, the superposition's phases become scrambled. This makes the system look like it has collapsed because interference effects disappear. Decoherence explains why superpositions seem to vanish in real life, but it doesn't pick a single outcome. The question of why one specific result appears remains open. In practical quantum technology, understanding collapse is very important. When we measure a qubit during a quantum computation, it forces the qubit into a definite state. This can stop the quantum process from continuing, so controlling measurement is key to building reliable quantum computers. Knowing how and when collapse happens helps scientists design better experiments and devices. So, in simple terms, measurement causes the wave function to jump from many possible states to just one. This process is fundamental to how quantum systems behave when we observe them. Even though we understand the basics, the full story behind collapse is still a mystery that scientists are actively exploring.